I'm going to continue to talk about 3.3 in this video, increasing, decreasing, and the first derivative test. This is part 2 of that section, okay? So really the focus here today is identifying exactly when we have relative maxes or mins. Now the term relative is not the same as absolute. A relative just means, let's take the example of a relative maximum. A relative maximum means it's greater than all the points immediately around it. It might be that down the line there's an absolute max, but that's still a relative. Now, on the other side, as long as we're talking about on the interior, let's not talk about endpoints right now, but relative, or excuse me, absolute maximums also are relative maximums, because an absolute maximum is going to be greater than all the points immediately around it. So relative min, relative max and a relative max, that would be a relative min, because it's less than all the points immediately around it. By the way, another term that we're going to use is also local. So if you ever hear me refer to a local max or a local min, that means the same thing as relative max or relative min. And on the flip side of that, if I ever talk about a global max or min, that's the same as absolute max or mins. And so when we talk about absolute max or min, it's greater than all the points. I should say greater than or equal to all the points, where a relative or local max is just greater than the points immediately around it on either side. Okay, so one way that we determine whether we have a max or relative max or min is the first derivative test. So given f is continuous on the interval containing x equals c, such that x equals c is a critical point. So going back to the last section, keep in mind a critical point means when the derivative is equal to 0, or when the derivative doesn't exist, but it does exist in the original f graph. Okay, so once again, we have to establish it's a critical point first. Derivative equals 0 or does not exist. Then what we're going to do is we're going to test either side. If f prime changes from positive to negative at x equals c, then f has a relative maximum at x equals c. So if you think about that, this is kind of logical. F prime changes from positive to negative. So what does it mean for f prime to be positive? Right? That means our slope is positive. That means the function is increasing, as we talked about in the other video. Okay? So if f prime goes from positive, f increasing, to negative, okay, then what we have is we have a maximum. So derivative goes from positive to negative. We're going to have a maximum at that point. And then conversely, if f prime changes from negative to positive at x equals c, so if our derivative is negative, f is decreasing, to positive, f is increasing, then what we have is a relative minimum at x equals c. If we do not see a sign change at our critical point, the derivative does not change, it goes positive to positive, negative to negative, then we have neither a max or a min, relative or otherwise. Okay, so let's do a couple examples how we're going to use this. What you're going to see is the way we analyze this for the first derivative test is going to be very much in line with what we saw in the first part of this section. Okay, so let's take a look at some examples. So first example, so for all these today, we're actually going to be doing the same thing. We're just going to use 3 separate functions. So we're going to find the x values of the relative extrema for f of x, and we're going to indicate whether each is a minimum or a maximum. So our first function, we start with polynomial. As I mentioned in the last video, we like polynomials. They're what we call well-behaved. They're always continuous. They're always differentiable. We don't have to worry about some of the weird curveballs that can come at us. In some of the other examples, we'll have something a little bit different here. Okay, so the first thing, basically what we're going to see from this analysis, we're going to see something very, very similar to what we saw in the last video that dealt with increasing and decreasing. So sometimes I'll give you problems where I ask you for all that. What intervals is a function increasing, decreasing, and then also where does it have relative max or min, okay? So the first thing I'm going to do is take the derivative of this and get those critical points, okay? So I'm going to find when this is equal 0. Make sure you show that as always. Factor out of 3x, that will leave us with x minus 4 equals 0. So I get two critical points, x equals 0 and x equals 4. So just like with intervals of increasing, I'm going to put that on a sign chart. Put both our factors. This will save us the time of actually calculating the values. We don't have to calculate the values. We just have to know if they are negative or positive. So pick a test point from each region. So -1, 1, and 5. And all we're going to do is determine the signs in each. So this is negative. This will be negative. Right? So the negative times a negative will be a positive. Okay? So this would be a positive. This would be a negative. Positive times a negative is a negative. 5, that's a positive. And that's a positive, so this is a positive. So if we were asking questions about whether or not it's increasing or decreasing, you can see that from here. Our function's increasing from -infinity to 0, and then from 4 to infinity. That is because f prime is greater than 0. And then we're decreasing from 0 to 4, and that is because f prime is decreasing. But from this I can also tell whether I have a relative max or min, because if you think about what's happening here, right, so this is increasing, this is decreasing, this is increasing, we can actually see that this is going to give us a max at x equals 0. And that is our first derivative test. Okay, so let's go ahead and write that up. We have a relative max at x equals 0 because f prime of zeros equals 0 and goes positive to negative. I start abbreviating quite a lot in these because, you know, we have to keep writing these things, and you do have to write these justifications. But, you know, it gets kind of redundant, but certainly, you know, for our uses here, we can abbreviate these things. By the way, if you don't restate that, as long as you're showing that here, that's fine. You do have to say it goes from positive to negative. Okay. Relative min. So we have a relative min at x equals 4 because f prime of 4 equals 0 and goes negative to positive. Okay, so that's basically it. That's the justification. That's what we want to show, exactly what I have here. I will tell you the sign chart is really just calculations for yourself. You don't technically have to do a sign chart. That just makes things easier in my opinion. But you do definitely need these justifications. Okay, I'm going to do two more examples. What I'll tell you is basically in each of these we're going to be doing similar things. It's just that we're going to get to some functions here that are a little bit more complicated. Okay, example 2, we're going to look at some trig values here. As I've mentioned before, these trig values are going to keep coming up, so we want to keep reviewing these. Unit circle, whatever gets the job done for you, but it is important that we're proficient at trig values. I went with a different labeling here, g of x, so please pay attention that we shouldn't be referring to this function as f. If I do that, that would be a mistake. Okay, now let me just point out that sine curves, they are also well behaved, so we don't have to worry about it. But here we're looking at an interval because of course these things are going to repeat themselves. So we just want to focus on this interval 0 to 2 pi. Okay, so g prime of x, looking for the critical points first. So 1/2 minus cosine x, I want to know when that's equals 0, okay? So that means I'm talking about when cosine x equals 1/2. You know, as I've mentioned, I'm a big fan of the unit circle, so we're going around the circle once. If cosine is equal to 1/2, that means we're talking about a radian measure, or excuse me, a reference angle of pi over 3. So we're slicing our units, which is pi, into 3. So pi over 3, 2 pi over 3, and then pi. And then on the other side, 4 pi over 3 and 5 pi over 3. Now, if cosine is positive, that means we're on this side of the x-axis, which means we're talking about these 2 points. So this is going to be pi over 3, which has the coordinates radical 3 over 2, 1/2. No, I'm sorry, it's the other way around. Okay. So that would be 1/2 radical 3 over 2, right? Cosine is x on the unit circle. And then over here, pi over 3, 2 pi over 3, pi, 4 pi over 3, 5 pi over 3. And that is 1/2, and then negative radical 3 over 2. Okay, so that's the point I'm looking at here. Okay, so now we have two critical points. So x equals pi over 3 and 5 pi over 3. So just like before, I'm going to make a sign chart. The only thing I want to indicate with my sign chart is we're beginning at 0 and we're ending at 2 pi. So we do not want, we also don't want to include 0 to 2 pi. The endpoints, when we talk about relative max and mins, we really don't consider endpoints like we do if we're talking about absolute maxes and mins. All right, so let's put on our critical points. So pi over 3 and 5 pi over 3. Now what we're going to do in each of these is we're just going to pick whichever is easiest. It really doesn't make a big difference. We just have to think through whether the value is positive or negative. So I'm going to pick, for instance, like pi over 4. Now from pi over 3 to 5 pi over 3, pi would be a good value to choose. And then for over here, I'm going to switch it around. I'm going to call this 7 pi over 4. Okay. So now we can't do what we did the polynomials. The polynomials are real nice in that regard. For this one, we have to just go with 1/2 minus cosine x. But it shouldn't be that big of a deal because we're using these trig values. It'll make it easier. So if I plug pi over 4 into that, I get 1/2 minus, and pi over 4 plugged into cosine would be radical 2 over 2. Now if you're trying to think about what that value is, what you want to realize is that radical 2 is going to be somewhat greater than 1. It's between 1 and 2. So what this means is radical 2 over 2 is going to be greater than 1/2. So if I take a number that's less than and subtract a greater, I'm going to get negative. Okay, so I know that's going to be negative. Okay, if I plug pi into cosine, I get negative 1. So this would be 1/2 minus negative 1, that would be plus 1. That's clearly positive. And let me point out, 7 pi over 4 just repeats this, right? Because x is still going to be positive, so it'll be 1/2 minus radical 2 over 2. Once again, we don't care about values here. All we care about is we're taking a lesser number, subtracting a greater number, so we're getting a negative again. And we see what we're going to have here. That means that our function g is decreasing, then it's increasing, then it's decreasing. Keep in mind, we're only going from 0 to 2 pi, and that is it. So let's go ahead and write this up here. So we have a relative min at x equals pi over 3, and that is because, and really focus on these justifications, they're very important, because f prime, excuse me, see, I did that. This is g prime. G prime of pi over 3 is equal 0 and goes negative to positive, okay? And we have a relative max at x equals 5 pi over 3, and that is because g prime of 5 pi over 3 is equal 0 and goes positive to negative. Okay, so I'm going to do one more example. In this function, we're going to be dealing with a function that has some differentiability issues. So let's take a look at that. Okay. Example 3, y equals the quantity x squared minus 4 to the 2/3 power. This is going to have some differentiability issues, which I mentioned, but it is continuous function. Keep in mind that when I have something to the 2/3 power, that means, and I think we saw this in the other video as well, we're going to take the cube root and then square it. Cube roots don't cause any problems as far as continuity. like we have with the even roots. Even roots, you cannot take the even root of a negative number. Odd roots you can, so we don't have that issue with having non-real values here. So we can just proceed and see what happens. So let's take our derivative, looking for our critical points. 2/3 comes down, x squared minus 4 to the negative 1/3. Got to make sure I pay attention to chain rule here, so this will be times 2x. I think it's a good idea to simplify this. So I would rewrite this. So let me point out that in the numerator we'll have 2 times 2, that's 4. And this x will be in the numerator. The 3 will be in the denominator. And this whole term, because that's a negative exponent, will be in the denominator. I'm going to write that as a cube root. So I'm thinking about what this thing actually means. Okay? Now, right away I have a critical point. So before I do anything, I know I have a critical point at x equals, actually I have 2, right? So I have 2 places that we're going to have a 0 in the denominator. 2 and negative 2 because of the square. So we have critical points at negative 2 and 2, and that is because y prime does not exist at those values. So as long as those exist in the original, and they do, we can take negative 2 and 2, which gives me 0. We can take that to the 2/3 power. So those do exist in the original, but they do not exist in the derivative. So those are critical points. But we still have to look if there's any critical points where this thing's equal to 0. Okay. Now, we don't have to think too hard about this, because realize that if I have a fraction equals 0, then I know that the numerator must be 0. So 4x has to be 0, or x equals 0 has to be 0. Or excuse me, x equals 0 will give us a 0 in the numerator. So this is because y prime is equal to 0 at that point. All right? So we proceed like we normally do. We don't worry about the fact that these critical points came from when y prime does not exist. For the first derivative test, we do it exactly the same way. So we have negative 2, we have 0, we have 2. Pick easy test points. Negative 3, I'm going to show you we don't actually have to take the cube root here, so we don't have to worry about whether we can take the cube root. Negative 1, 1, and 3, that's going to work fine for us. Now, I am going to go ahead and look at the factors. Really, this is going to work similar to when we factor a polynomial. We have a numerator and a denominator. If one of them's negative, then the result will be negative. If one of them is positive and the other, or excuse me, if one of them's positive and one of them's negative, we know it's going to be negative. If both are the same sign, positive, positive, negative, negative, then we know that the derivative will be positive. So all I'm going to look at is the numerator, which is 4x, okay, and the denominator. But let me just point out that really all I care about from the denominator is the x squared minus 4, because whatever goes into the cube root, if it's negative, the cube root will keep the negative. If it's positive, the cube root will keep the positive. So this is going to determine whether the denominator is positive or negative, okay? So I'm just going to look at that. Okay, so let's plug negative 3 into 4x. That's going to give us a negative. Negative 3 plugged into this, well, that's going to give us negative 3 squared is 9. 9 minus 4 is 5, so that's positive. So this is going to be negative. Now if I take negative 1 into that gives me a negative. Negative 1 into this, well, that's 1 minus 4. That's a negative. Negative times a negative is a positive. Okay? 1 goes in. That's going to give us... Wait. Oh, yeah. 1 goes in. That gives us a positive. 1 goes in here. That still gives us a negative. So this is a negative. 3 goes in there. That's a positive. That's going to give us a positive. So this is a positive. Okay? So we have decreasing, increasing, decreasing, and then increasing. So what this tells us is we have 2 relative mins. Those occur at x equals negative 2 and 2. And we have 1 relative max. Okay, So let's go ahead and write that up. So relative min at x equals -2 and 2. That is because f prime does not exist. Now, like I said before, it's a bit redundant because I already dealt with that, but that's fine because f prime does not exist. And it's not f though. Getting bad habits here. That's a mistake that if you do make, I don't tend to ding you on. I will tell you that down the line, variable agreement, and that would be variable agreement, is something I want to pay attention to. So this is y prime does not exist and goes negative to positive. Okay, so we have a relative min at both of those values here. Okay, so now we're gonna do our relative max. So now we have a relative max at x equals 0. That is because y prime equals 0 this time and goes positive to negative. Hopefully my handwriting isn't too messy. Once again, these justifications are very, very important. Make sure we see all that. Okay, so that's it for section 3.3.